So let me start by recalling some elementary fact. So let me start with Poincaré inequality, which hold in any metric space due to the fact that it holds on the real line. So the result is there exists a constant, universal constant, C naught, such that if you take any S, which is greater than 0, if you take alpha, which is in W12 of 0S, such that then you have that the integral from 0 to S alpha dot square dt is greater than C naught over S square, the integral from 0 to S alpha square of t dt. And so smaller is S, beta is your constant. A consequence of that, I am going to write a Hilbert space version, although it is true in any metric space. Let H be L2 of omega Rd, where omega is 0, 1 to the d. And let P be in W12 of 0S H. Be such that P at time S is identically null. Then the integral from 0 to S P dot square dt is greater than C naught divided by t square, the integral from 0 to S P square dt. And the norm of P Thank you. S. This is the integral over omega P of t x square d omega. So let us recall what the Newton's law, for which we're trying to construct a solution. The data is assumed that t is greater than 0, and assume that I have f and u star from the torus, cross the set of probability measure on the torus into R, which is Lipschitz. And I'm going to add more condition later. So problem. given a measure mu, a probability measure on the torus, we want to find S from 0t cross 0t cross the torus into the torus, such that the following Newton's law is satisfied. The second derivative with respect to time of S of t sq equal to negative the gradient with respect to q of f of s of t sq s ts push forward mu sigma t dt s of 0 sq equal to gradient u star of s of 0 sq sigma 0 s of q equal to q, where I set sigma t equal to the push forward of mu by s. In fact, sigma t depends on little s, but I am not going to display the dependence. And we use the notation since S is in fact a function of t s q mu, we write S equal to sigma S, which is the initial condition, t, which is a variable, mu, to say that this is the density of the distribution of the system, and this is a map from the torus to the torus. And we want to prove existence, uniqueness, and regularity of solution. So as usually done, let me write this into integral form. If S satisfies that equation, then S the derivative with respect to t of S of t S q is the derivative with respect to t of S of 0 sq plus the integral from 0 to t, the derivative, second derivative of S of tau sq d tau. So if S satisfies the system, then it must satisfy that equation. Now, I am going to replace the derivative at time 0 by what is there. So it will be the gradient u star of S of 0 sq sigma 0 plus. Okay. If the derivative of S with respect to t satisfies that, then S of t sq will be S of S sq plus the integral from t to s of the derivative with respect to time of s of L S Q dl. And I am going to substitute this here. That will be equal to S of S as a Q is a Q. So that will be equal to Q plus S minus T gradient U star of S of 0 SQ plus the integral from 0 to T d tau, the integral from 0 the integral from S, from T to S, dl, the integral from 0 to L, the second derivative of S, but the second derivative of S is negative gradient Q f of S tau S Q sigma tau d tau. So I think here it will be the derivative from the integral from S to T. It will be the integral from S to T. And with a negative sign, it will be the integral from T to S. Okay, so if I define an operator M, which will depend on S and mu, S, T, SQ, if I define an operator MS, solving my system of equation is equivalent to finding a fixed point. Therefore, Newton's law is equivalent to finding a fixed point of M. And here there is something which is missing. There is sigma naught. And this sigma naught, according to that definition, it is S of 0, S, push forward mu. And the sigma tau is S of tau S, push forward mu. So if the gradient of U star is continuous, the gradient of F is continuous, then S continue make this whole thing continuous. And so my operator M is an operator from the set of continuous function to the set of continuous function. Now I am going to make the following assumption. Gradient Q, F, gradient Q, Q, F, gradient Q, 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 F, gradient Q, U star, gradient Q, Q, U star, gradient Q, 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 U star exists and are continuous. In both variables. Therefore, since they exist and they are continuous, they are bounded by a constant. So I am going to assume that F and U star are kappa Lipschitz. If they are kappa Lipschitz for a constant kappa, then they are kappa Lipschitz for the maximum of the constant kappa and 1. And so it is not a loss of generality to assume that kappa is greater than or equal to 1. Now, here is one difference between what we have done and what Pierre Louis-Lyon, Lasry, Cardier-Laguette, Delary have done. We have assumed that our F and U are from a potential function. And so, under that condition, you can show that solving this problem is solving a minimization problem. So it means that what we are doing is what is called a potential mean-field game, when the data are derived from a potential. So we assume that there exists F and U star from the set of probability measure into R, such that if you compute the Wasserstein gradient of F and you apply it to mu, then it is gradient Q F mu. And if you compute the Wasserstein gradient of U star mu, then it is a gradient Q of U star. So for examples, assume F and phi are function of class C infinity on the torus. Set F of mu to be the integral on the torus F convolution mu d mu. In that case, the Wasserstein gradient of F at mu is the gradient of F convolution mu. And so I am the equality holder if I choose F of Q mu to be equal to. So this should be 1/2. This is 1/2. To be equal to F convolution mu. And the same thing if you choose U star of mu to be 1/2, the integral on the torus phi convolution mu d mu. then the gradient of u star at mu is the gradient of phi convolution mu. And u star is the phi convolution mu. So now I have two options. Either I will continue listing the assumption. There is a long list of assumptions. Or I will assume in the sequel that I am working with this function. And the condition I impose here will be enough for what I want to do. And in fact, you just need C4 here. So let me assume in the sequel that this is what I am. This is the assumption I am making. So in my work with Anjay, we've done most of the thing with quite a general U. And just to prove the regularity of the function S with respect to the mu variable, we work on such example, just to avoid the technical difficulty. But the proof should be valid in a greater generality. In the sequel, we restrict ourselves to this example. Theorem. If T is small enough, then Newton's law has a unique solution. Such that in W to infinity of 0t cross 0t cross TD. But in fact, S will satisfy better regularity property. Furthermore, mu goes to S T Q mu goes to sigma S T mu of Q is W to infinity. So, idea of the proof. I want to show that my map has a fixed point. And so M mu I will consider that as a function from the set of continuous functions on 0t cross 0t cross the torus into 0t cross 0t cross the torus. But that will not be enough because this is not a compact set. So I am going to restrict myself to function. Let CA be the set of S such that the following condition hold. So you can guess where I am getting this condition from. I am going to impose that S, the L infinity norm, is less than square root of d plus 1 over 2. The derivative of with respect to time of S is less than 2 kappa. The second derivative of S, the gradient Q of S, the second gradient Q of S is less than A. The gradient TQ of S is less than 3/2 kappa A. So what you do is you try to put a fixed point problem and property, and then you look what are the conditions. You start checking S, if S satisfies some inequality, what will the range satisfy? And then you see that it suggests how to choose this constant. ds sigma is less than A. So I am going to put it here, dss is less than A. dts s is less than square root of 2 kappa 1 plus t A. So observe that if I take t very small, this I can compare t to square root of 2 kappa A. So note that when I choose this, I am going to assume that all derivative, gradient I phi, gradient I f, are all less than kappa. So you can see from them that no matter how I choose S, ms will be less than. Observe. ms mu of S in absolute value. The largest value which Q can take in the torus is square root of D. This is less than S minus T kappa plus, if you integrate that, you will get something which is less than t squared over 2 kappa. But s minus t is less than t. So if I take t small enough, then this condition will be satisfied. So maybe it is better. I think you have over 2. I think the norm on the torus is, I take the torus of length negative 1 half to the d. And the norm will be less than square root of d over 2. So if you differentiate, for instance, s with respect to t, you get for free a bound. If you differentiate with respect to s, you get for free a bound. And so you can check that ms, one checks that m of mu is a contraction from C star A into C star A if T is small enough. S M mu S equal to S has a unique solution. And the solution has this regularity. And you will check that this regularity are enough to improve the regularity to W to infinity. So for instance, here, dSS of S is missing. And so you will check that with this you can get that control. Now, what remains is the regularity with respect to mu. So I am going to look at 1 over n, sum I from 1 to n, delta Si, where S1, Sn belong to the torus. This is a subset of a set of probability measure on the torus, and the union of this set is dense in the set of measure preserving map. So the idea is to study the restriction of M to this set and find the estimate which are independent of N. And so you let N go to infinity. So on this set, if you construct a Lipschitz function, for instance, you can extend them on the whole set with the same Lipschitz constant. If the Lipschitz constant is independent of N, then you can pass to the limit and say that up to a subsequence, you have a limit which is satisfy the same regularity property. Now, you are going to check that the limit is a fixed point of your map. And so since it is a fixed point of your map, you have concluded that the fixed point has this nice property. So here is what you do study S of T S Q S1 Sn equal to sigma S T 1 over n sum I from 1 to n delta Si of Q. So this map makes sense. If I want to study property of this map, I can start with the following. Let me write this of the form S of T defined inductively starts with S naught from 0t cross 0t cross the torus cross the torus to the power n into the torus to the power with the dimension of torus. Define inductively Sk plus 1 equal to m S 1 over n sum I from 1 to n delta Si Sk. Okay. So this sequence, because my map is a contraction, this sequence for n fixed, when k goes to infinity, will converge to the unique fixed point. So you start with S naught. You show that if Sk satisfy, I want to show this. I want to show that the gradient Si, Sj, I assume that it is less than a constant which depends on A divided by n squared. So this scaling is the correct scaling. If I have a two derivative, this scaling is the correct scaling. For I is not J. And gradient Si, Sk is less than Ca divided by n if I is J. So I am going to show that find Ca such that if Sk satisfies the above, so does Sk plus 1. And you can check that such a constant exists. And so when you let k go to infinity, you get that your fixed point satisfies this estimate. One over n is what corresponds to, so let me make the following observation so that we understand. Observation. Phi f of mu x will be equal to 1 f of 1 over n, sum I from 1 to n, delta Si. Okay. So I take f as before, and this will be 1 over 2n squared, sum I equal to 1, ij, phi of Si, f of Si minus Sj. So when you compute the Wasserstein gradient of mu, and you compare it to the classical gradient, it is, so here is, let me, according to what I wrote before, the Wasserstein gradient, f mu x, is the gradient of phi composition mu x. So the Wasserstein gradient at Q is 1 over n, sum I from 1 to n, gradient phi Si Q minus Si. No, this is F. This is F, and that is F. Now, compute the gradient with respect to Si of f of mu x. According to what is there, it is 1 over 2n squared, the sum I from 1 to n, Q, gradient f, Q minus Si. So I differentiate what is above. So Si, J, Si minus Sj. Now compare this to that. Here I have a coefficient 1 over n, and there I have a coefficient n squared. This is not an accident. You can prove rigorously that there is a relation between the Wasserstein gradient and the classical gradient. Facts. If I take any arbitrary smooth function and I write the Wasserstein gradient, the gradient with respect to Si of a function f, 1 over n, sum I from 1 to n, delta Si, at Si, what you get is the Wasserstein gradient of f at 1 over n, sum I from 1 to n, delta Si, with a coefficient 1 over n. So this is not an accident. This, the relation between the Wasserstein gradient and the capital gradient produces 1 over n in front of that. And so this is to tell you that this coefficient, this bond I have, the correct, if you want to have a bond which is independent of mu, the correct estimate will be a constant divided by n squared. the above estimate, the estimate gradient Si, Sj, S is less than Ca divided by n squared. Gradient Si, Si, S is less than Ca divided by n. Translate into the fact that the Wasserstein gradient, the second Wasserstein gradient of S of sigma S T mu is less than Ca. So when mu is in the set 1 over n, the sum I from 1 to n, delta Si. So if you look at the restriction of that map to this discrete set, then this estimate translates into that. And you have the same conclusion that if I differentiate with respect to the first variable, I have something which is less than A. And so I can extend my map to obtain a Lipschitz map with the same constant. And then I let n go to infinity, and I show that my limit is the unique fixed point. Okay, so to finish, so I am going to move to something which relates to Hamilton-Jacobi equation we are familiar with. So for Hamilton-Jacobi, on the set of probability measure. For T in 0T and mu, a probability measure on the torus, define the value function U of T mu is the infimum over sigma and V. The integral from 0 to T L of V S sigma S Vs dt plus U star of sigma 0. So here what is L? Here L of sigma S Vs is 1/2 the integral on the torus of V. So I'll call it tau, V tau. Of V tau x squared sigma tau dx. And plus f of sigma tau So I have a minus. I have a kinetic energy minus a potential energy. And I define this value function. So there are three definitions of viscosity solution which have been proposed. There is a one which is proposed by Andrzej Switch and myself, which work only for function on this form, depending on the norm of V. And there is one proposed by Tudorescu and myself, and there is another one proposed by Ambrosio and Feng. And for these three definitions, this value function is a viscosity solution of the Hamilton-Jacobi equation, where the Hamiltonian is in L, you replace negative by plus. So here is what I think to remark, which are worth mentioning. Set this x in 0t. Set sigma t to be sigma s t mu, and v s t of mu to be the derivative respect to term of sigma s t mu. Composition with sigma s t of mu inverse. So, theorem. The first statement is, let me put a bar here. Sigma bar V S mu is a minimizer in the value function. So when I fix x as my endpoint, I minimize the path going from 0 to s, given by this, is a minimizer in my value function. And we learned that dt sigma bar plus divergence of sigma bar Vs t mu equal to 0. Now, here is an important observation. I have my sigma bar. I have a V is admissible. This V is admissible. I can replace it by another V. Right? If you give me this, there are several V which are solution to that. So if I take a Vst mu and I add a W to it such that the divergence of a sigma bar W is 0, this is another velocity which is admissible. Now, if I am minimizing this, it means that among this W, I am going to take the W which is going to give me the smallest L2 norm. If mu is absolute continuum with respect to Lebesgue and is positive, this is Hodge decomposition. Hodge decomposition says that a consequence of the following lead to Hodge decomposition. If I take a positive measure, you give me a function, and I minimize. I impose the divergence of this by the vector field is prescribed, then the smallest velocity will be the gradient of a function. Because of the gradient of a function, it is a gradient of a function, then it is the gradient of it is symmetric. So last time I told you that the gradient of a VST equal to the gradient of a VST transpose. It is because formally VST is a minimizer of that problem, and the minimizer of that problem must be the gradient. Now you will need to worry and say, what if my sigma t is not absolutely continuous with respect to Lebesgue? What you know is the gradient of a VST mu will be bounded by a constant which is independent of mu. So in particular, if I take mu n absolutely continuous with respect to Lebesgue, I will have that for a short time, I will have that the path will stay absolutely continuous with respect to Lebesgue. And so this velocity will be gradient of function. Because I have such an estimate, when I pass to the limit, my limit will remain a gradient of a function. And so you have this result in general. One other thing which is interesting to observe is we prove that if you compute the gradient of this value function with respect to the Wasserstein metric, and you compute the gradient of the solution of the master equation, at mu, then these two things are the same. So how do you prove that? If I want to prove something like that, for those who are familiar with Hamilton-Jacobi equation, there is no surprise that this is the velocity, SS. So I'll put sigma t. Sigma t. And there is no surprise that the gradient of the value function equal to the velocity of your system. But last time we showed that the velocity of our system is the gradient with respect to q of u, and so you get that the Wasserstein gradient of the value function is the space gradient of u. So something we can learn from that is the search of u is a Nash equilibrium problem. It is not a minimization problem. But what has been established here is behind this equilibrium problem is hidden a minimization problem which can allow you to construct a solution to construct equilibrium. So I realize that you find this to be very easy to follow. I apologize if I cannot keep going on, and I'm going to stop here.